Let's dive right into this explainer. Transitioning autonomous AI agents from flawless, polished demos into actual, real-world production environments is uniquely brutal. For the past couple of years, we've seen this incredible evolution, right? We're moving away from simple conversational chatbots to these goal-driven agentic systems that perceive their environments, keep track of internal states, and actually execute actions using external tools. The promise is absolutely massive. But as anyone actually building these systems will tell you, the leap from a controlled demo to a live, messy production environment is a completely different beast. Gartner put out this staggering prediction that half of all AI agent deployments will fail by 2030. But here's the catch. These aren't your standard software bugs. Think about it. If a traditional piece of software fails, it throws a syntax error or gives you a nice clear crash report. But with Agentic AI, the failures are often entirely semantic. The agent might hallucinate a fact, misinterpret a basic instruction, or silently corrupt its own memory. So, to your standard monitoring tools, everything looks perfectly normal and healthy, while the agent is actually steering the entire process straight off a cliff. There is just a stark contrast between the clean, safe assumptions of an agent demo and the harsh reality of production. In a demo, we assume bounded contexts, perfectly clean handoffs between agents, and nice linear chains of thought. But in reality, we get silent, cascading hallucinations. We see context exhaustion, where the agent's reasoning completely degrades long before its context window actually fills up. And we see topology collapse, where just one faulty agent brings down an entire multi-agent network. It's literally an entirely different physics of failure.
Part 1. The Infinite Loop Trap. With agentic systems, these loops are semantic and probabilistic, rather than just basic syntactic errors.
Now, unlike a traditional program that hits a predictable logic error, like a while loop missing a break condition, an agentic loop is way more insidious. You might be wondering, why do highly intelligent agents just get stuck in repetitive actions without making any actual progress? Well, it usually boils down to a lack of proper termination conditions and progress tracking. The agent generates thoughts, selects tools, processes what it sees, and genuinely believes it's making progress. It makes search for a document that simply doesn't exist, but because it doesn't know the document is missing, it evaluates the vague results, replans, and just searches again. It's trying the exact same failed strategy over and over because it lacks the milestone awareness to realize, hey, my approach is fundamentally broken. These agents fall into some really specific, frankly fascinating traps. Everything from endlessly querying for a non-existent document to two agents getting completely locked in a deadlocked negotiation. For example, in coding tasks, we see what's called the death spiral. This is a modification validation loop where a model finds an error, changes the code, sees a new error, and blindly reverts its changes, just bouncing back and forth forever. In multi-agent setups, you get the deadly embrace. Agent A delegates a task to Agent B, but Agent B needs info from Agent A to even start. So they just sit there, constantly messaging each other, burning through tokens at every step of their infinite standoff. And without explicit termination conditions, an agent trapped in one of these recursive reasoning loops can rack up thousands of dollars in API costs before anyone even notices. It's been called the denial of wallet attack for the AI era. There's actually a documented case where an agent hit a weather API 843 consecutive times. Why? Because it somehow decided the JSON response was incomplete, even though the response was perfectly valid and identical every single time. At scale, an agent looping 10 cycles per minute with a massive context window is going to drain your infrastructure budget with terrifying speed. Part 2. Planning errors in long horizons. We really have to look at the cognitive dissonance between an agent's ability to reason locally versus its ability to plan for the long term. Reasoning is just generating a locally coherent thought. Planning is accounting for the delayed consequences of actions over time. Just because a large language model can reason brilliantly in a single conversational turn does not mean it can successfully navigate a complex, multi-step objective. Agents frequently fall into myopic traps. They pick actions that look perfectly logical for the immediate next step, but inevitably introduce dependencies that cause a total crash 10 steps later. Imagine a software engineering agent picking a specific library because it perfectly solves the immediate code snipping in front of it. That's a greedy, short-term choice. It completely ignores that this library introduces a dependency conflict that will obliterate the validation phase way down the line. It was highly confident in its local reasoning, but completely blind to the global outcome. When we look at data from the Web Arena Lite benchmark across a variety of models, the dominant failure mode is just getting stuck midway through. This really proves that out-of-the-box models lack the milestone awareness to sustain long-horizon execution. Nearly 50% of the time, whether you're using a proprietary model like Gemini or an open one like Gemma, the agent just gets stuck.
It pushes forward, loses the plot entirely, and starts to oscillate. It fundamentally fails to update its internal state or recognize what its next logical milestone needs to be. Part 3. How early errors cascade. In a long horizon task, a tiny ambiguity right at the start, like an undefined term in the prompt, cascades into false assumptions. This is the underlying physics of agent failures, the classic domino effect of error propagation. Let's say you tell an agent to remove outdated entries from a database, but you never clearly define what outdated actually means. The agent is just going to hallucinate its own definition. Maybe it assumes anything older than 30 days is outdated. It acts on that false assumption, and by step 20, that initial specification error has compounded into a catastrophic failure where critical data has been irreversibly deleted. A small mistake early on isn't just a minor blip. It becomes this foundational error that the agent builds all of its future reasoning upon. The reasoning looked totally correct, but the initial premise was fatally flawed. These failures emerge from system-level orchestration flaws, where probabilistic models catastrophically clash with deterministic external environments. And this data, pulled from an analysis of over 1,600 annotated production traces, tells us something incredibly profound. Throwing a bigger, smarter, more expensive model at the problem, it literally will not fix it. 79% of the time, the system breaks because of specification ambiguity, breakdowns in coordination between agents, or task verification failures. This is a structural engineering problem, plain and simple. We even have industry validation from Microsoft's AI Red Team showing how failures in generative AI get vastly more complex and damaging once we introduce autonomy and tool use. When an agent can actively interact with an environment, when it has excessive agency or insufficient isolation, the stakes skyrocket. It's no longer just spitting out a slightly wrong text summary. It's potentially processing a rogue termination in an HR system or dropping an active database table because it misinterpreted a user casually saying, "Get rid of it."
Part 4. Governing agentic AI systems. Because outputs vary and meanings can drift so much, informal governance is just impossible. You absolutely cannot just deploy an agent and cross your fingers. You have to explicitly bound its autonomy, or you completely lose the ability to predict its behavior and control your financial exposure. To prevent the math of ruin, we need to explicitly cap iterations, enforce semantic circuit breakers, and seriously stop shoving every single instruction into the prompt by using structured, verifiable subgoals instead. You need hard limits, like say 10 to 30 cycles, before the system just cuts the agent off. You need loop detection, checking the agent's memory to see if it's just rephrasing the exact same failed search query. And for high-stakes actions, you absolutely need human-on-the-loop escalation. Let the agent have the autonomy to plan, but require a real human to verify everything before actually pulling the trigger. So, I'm going to leave you with this question to chew on. The next generation of AI agency won't be defined by the raw computing power of the underlying model. It's going to be defined by the safety and resilience of the structural harness you build around it. Are you just letting a probabilistic model run wild, hoping it navigates the rigid, deterministic world safely? Or are you engineering a real system with explicit circuit breakers, robust state management, and clear subgoal verification? Because mastering that harness, that is the only way to successfully graduate from the flashy demo phase into reality.